Thank you very much for very interesting talks. I was wondering, from like a public perspective as well, often with new technologies, something people worry a lot about is safety. I know there have been some stories of lithium-ion battery fires and so on. I wondered what kind of technological developments are happening in that kind of space, and if we're doing any work on that.
Who wants to take that one? Maybe that's one.
Start on that one. So lithium-ion batteries, if you abuse them, if you take them well beyond the way in which they're supposed to be operated, can catch fire, and they can do so with quite a lot of energy. So the products that you see on the road today, the cars that you see on the road today, have been very carefully designed to make sure that those batteries are kept well within their safe operating conditions, and that they're protected in the vehicle in very much the same way that you would protect an occupant in the vehicle. So only the most extreme of events would lead you to that kind of situation. Now, the challenge that we've got is obviously to do that introduces a cost overhead and a weight overhead to the vehicle. So if we're able to develop batteries which don't have some of those failure mechanisms, we can take advantage of that by making the vehicles lighter and cheaper and have more flexibility over the design of the package. So there are technologies, so Serena mentioned earlier things like solid state technologies, which take the volatile organic compounds, the liquids that can burn out of the battery and replace them with things like ceramic layers or polymer layers. So there are some things that we can move forward on that, but I would encourage you to think, safety is not something that we optimize. Safety is a threshold that we have to achieve. What we optimize is how much energy or how much cost or how much performance we can get within an acceptable level of safety.
Does anyone else want to come in on that? We'll go to another question if not.
Really quickly, just on, you do see these pictures spreading really quickly on social media, right? Like of a battery on fire. Very many more cars go on fire because of petrol. So I think we should state that. But yeah, there are developments, and Faraday Institution is leading on projects to look at ceramic materials that can withstand very high temperatures and still allow for lithium to be going across your battery very safely.
And just quickly on that, on a cell level, high quality raw materials, better processing methods, improving the battery cell level drastically. But interestingly, on a pack level, you're starting to see introductions of like flame retardant materials within the pack to stop the propagation. If a cell fails, it catches on fire. You can shut that off through the management system, but actually this flame retardant material within the pack can kind of stop that propagation. So, but that's a real big area of R&D and interest.
Are there any disruptive technologies on the horizon? And B, could you spend a little more time on the end of life?
Disruptive technologies. I don't know who wants to tackle that. Serena, is that one for you?
That is a really challenging question, because I think depending on who you speak to, every individual will tell you that their particular chemistry is the next disruptive technology. I think one of the things that could have the potential to be very disruptive could be additives that we put into electrolytes that help heal or protect electrodes, and they prolong the battery life so that you don't see, in your last slide, Judith, you had this, the decrease in capacity over time. And if we can come up with suitable additives that protect the battery against those sorts of degradation mechanisms that cause that decrease in capacity over time, I think that has the potential to be very disruptive.
And on that, lithium-ion batteries are getting better. So they're pushing these technologies further down the timeline, as Judith was saying. So new chemistries, new formulations of NCM is pushing even the solid state further down. And it's very important not to read the headlines that are coming from the universities, with all respect, because that's where the R&D, that's where the stuff is happening on the R&D basis. But it takes a long time to commercialize that and get it into the supply chain, and that's a really important point.
Yeah, I would say so. The word disruptive is a really salient one to use, actually. If you look at the next generations of battery chemistry that are coming down the pike at the moment, and the timeline that Judith outlined is exactly the right one. Nobody knows how long a battery takes to come out of academia, because it might never come out. But once it's popped out of there, there's a reasonably predictable timeline for how it gets to market, and it's the timelines that Judith described. The question of whether it's disruptive to me is, could I accommodate it within my supply chain? So in other words, if I've built a gigafactory And all I need to do is change one grey goo for a different grey goo, and everything still works. And okay, the supply chain bit needs to sit in. To me, that's not very disruptive. It's certainly evolutionary. It certainly improves significantly the performance of the battery. But actually, the next generations of chemistries that we're working in the labs mostly fit that mold. So things like sodium-ion chemistry that could potentially reduce the cost significantly, even some of the solid states technologies could actually fit the majority of that manufacturing process and wouldn't be too disruptive. Where we start to step off that curve into something which is radically different in its design is where we start to get into things like the lithium-air batteries, which actually function in a very different way. They breathe a bit like an engine or a fuel cell. And then really you would worry that you'd made a huge investment in a massive gigafactory and suddenly it's no longer fit for purpose.
Okay, we have a question here. Can we have a microphone over here, please?
What's the strongest kind of battery you know?
Strongest kind of battery you know. Who wants to take that one?
So we work with things for motorsport applications. So the cars that Judith showed are fast, but the kind of things that we're talking about are the kind of things that run around Formula 1 tracks or run around Formula E tracks. And there we're actually developing the battery in a very different way, because it's not about how far the car can go, it's about how fast it can go. So we're tuning those batteries for power instead of for energy. And interestingly, the whole way that you design for the chemistry and everything else changes in order to do that. But they're still lithium-ion batteries at heart. They're just moved around a bit in the way that we designed them.
What's your name?
Max.
Max? That's a really good question, because it stumped us all, actually, because on the for a vehicle, for a car, lithium-ion batteries right now are the best that there is, and they're getting better on a cell level and on a car level, on a pack level. But things like energy storage, where you can plug your house into a battery, there are quite a few different technologies and types, flavors of batteries, including different flow batteries, even saltwater batteries have been mentioned. So that arena for powering your house is a completely open arena for batteries. Good question.
Great question, thank you. Yes, take one here.
You always see these headlines on Daily Mail and stuff saying Elon Musk is killing the world because he's mining for the materials for these batteries, but how environmentally damaging are they?
Simon, do you want to tackle that?
Cheers. Good question. I mean, from a supply chain perspective, let's look at lithium, for example. A third of lithium is coming from brine resources, actually quite low impact, but quite intensive on water, using water from the local area. Then you look at graphite mining, it's traditional mining, it's quite dusty. But my point is, all these raw materials are coming from the same place the raw materials that make all the car components are coming from. In fact, there's a lot less components that go in an electric vehicle than there are in a gasoline vehicle, an ICE vehicle, far less. So it's another argument about the energy you put into the battery to fuel it. That's probably something for someone else. But from a battery supply chain perspective, because there's far less components and lithium coming from brine resources is quite a big component of that, I would argue a lot less environmental impact from the mining perspective. But everything's got to come from the ground, whether it's an electric vehicle or an ICE vehicle. And that's something to consider, which is why recycling is such a big part of the whole supply chain.
In the traditional model we've grown up of producing vehicles, the idea is the more you produce, the less they cost per unit, or you can add frills and things on for the same cost. It seems to be what you're saying with these giga ones, and then logically latching on the rest of the reduction to it, that the more you produce an unlimited amount of ethically sourced material, the more you produce, the more you shove up the unit price.
So from a manufacturing perspective, clearly the same rules of economy of scale apply to an extent, which is why the gigafactories are the size they are. But that only covers the cost of converting the raw materials to the final product. And clearly, as the market ramps up, and Simon showed the scale of the ramp up the market needs to achieve, you're going to see times in there where the supply and demand get out of kilter with each other, and that is inevitably going to drive some price fluctuations. So the issue might not just be that the price could increase at times, but also that it might not be terribly predictable. I think Simon's probably a better place to comment on that.
On the ethical side of things, usually if you want ethical raw materials, the price goes up. It's a really good point. Cobalt's a perfect example. For instance, cobalt, Casper, 70%, 65% is a DRC. 70% of cobalt comes from the Democratic Republic of Congo. There aren't any big cobalt mines outside of the Congo. It's just a geological curiosity of the world. So if you want guaranteed ethical cobalt, then you can't be sourcing from the Congo, but then at the same time you want scale. So then what do you do next? You try and build new mines outside, but they're going to be more expensive. So I agree, certainly on the cobalt side and for probably other raw materials that are sourced in China, like graphite, for example, ethical means a higher cost at a time when everyone wants cost to go down.
I think there was a question here.
Could you say a bit more about batteries for general energy storage, electrification, because power generation, I think, is a much, much bigger thing to worry about than cars?
So at the moment, from a battery industry perspective, cars is where it's at. And the reason for that is because cars are a market which are very highly regulated towards reducing their CO2 and their pollution. The technology has got to a point where it can start to answer that question, albeit at a relatively high cost point, and the volumes are very significant. So right now, that is, if you're a battery manufacturer, right now, that's the market that you really care about capturing. Now, in theory, grid scale energy storage could be about the same size or even a larger market. The challenge is it's a slower one at the moment, and the regulatory regimes in many countries, the UK included, are such that actually ownership of energy storage assets is quite difficult within the system. So our current regulations do not allow distribution network operators to own batteries because they're classed as an energy generation device, and the regulator wants to separate generation from distribution. So the one organisation in the UK that could take a benefit from owning that device is prohibited from using it, from buying it. So it is a really important market. It will come. It may not use the same technologies that we develop for cars. In cars, we care a lot about safety and the compactness of the battery. If you're going to put your battery in a large remote building connected to a wind turbine, you can deal with things like safety differently. You don't care about mass, and you probably don't care about volume so much. So there are very different technologies that we would start to develop for those when the market builds to be ready for them.
In the last few years, the energy storage industry globally has grown fourfold, but it's from a really low base. It's like 5 gigawatt hours worth of battery market last year. It was about 160 gigawatt hours, of which nearly all of those were lithium-ion batteries. And that's not necessarily because it's the best fit for the purpose. It's because it's available and the cost is coming down. Other battery technologies that are competing in the space, as I mentioned, lead acid, vanadium flow. But for me, the scale of the build out of these battery mega factories will mean the availability will go up, the cost will come down, and that market will emerge, lithium ion will emerge in that market even stronger, I think.
This is related to the last question, but could you say a word about the power infrastructure required to recharge the car batteries? First of all, the power stations or renewable energies which will be capable of supplying that, and secondly, the distribution networks.
Mm-hmm. Would you like to pick that up? So the first question, the first part of that question, I think, is, can the grid cope? Is there enough electricity out there to charge all of these vehicles? I think that the simple answer to that is yes, as long as we don't all plug them in simultaneously. And actually, that's quite, whilst it seems superficial, actually, it's quite an important point. So as the market grows, dealing with 1 million or so vehicles on the road is not that difficult. Even if we all come back and plug them in at 5 o'clock in the evening, there is enough capacity remaining with the generation network and the high voltage distribution network to deal with that. Unfortunately, if we do it, we push the generating resources to their maximum limit, and at that point we start to bring back on stream things like coal, which we've typically been trying to turn off in order to get the CO2 balance back. If, on the other hand, we can coordinate the charging of vehicles to take place particularly overnight or during the day when there's much less demand on the grid, then we do so much more cost effectively with lower carbon and in a way which is quite perfectly manageable by both the grid and the vehicle. So I think at the overall power generation level, I'm not terribly worried. Even with the grid as we have it today, there's enough capacity to be able to support pretty much a total fleet. However, we have to get it from where it's generated to where it's used. And whereas the high voltage network, the 400 kV grid that the National Grid operates, is sized around all of the power generation that we've got, when you come off that and start to distribute it around to houses, you're using an infrastructure, much of which was put in place in the 1930s or thereabouts, when the average power consumption for a house was, the average maximum power consumption for a house was 1.5 kilowatts. So in other words, the people putting the copper in your road hope that if you put your kettle on, the person in the house next door doesn't. And that infrastructure has been well used over a long period of time, and that asset has been sweated. And we're at the point now where some of the substations at the end of your road rely on cooling down overnight in order to be able to manage the rigors of the next day. And of course, if that road then produces a lot of electric vehicles all charging overnight, then we take away some of that. So my concern is less with the overall generation of power. I think that's a manageable issue. We do have some challenges. We need to get some signals protocols between charging cars and grids to say when's good and when's not, but that's not rocket science. But I'm much more worried about the local infrastructure, how we go from the high voltage grid down to a service station with a load of fast chargers on, or to a road full of electric vehicles that's got a 1930s housing stock.
Okay, I think we had a question up here somewhere.
Yeah, the question I was going to
possibly
ask.
two. I don't know if there's.
Sorry,
do you want to ask one as well? Yeah. So one up there, and then one down here.
The question I was going to ask kind of fits into the direction of the conversation, which is historically there's been a lot of talk about fuel cells and hydrogen as alternatives to internal combustion engines. Do they have a role with the battery, or is it just exogenous generation of power and then storage in a battery, or do you have other kind of propulsion devices in a car? As I say, maybe a fuel cell or a hydrogen source.
So I'd say a battery has a role in a fuel cell. So typically a fuel cell is sized to provide the average power of a vehicle, and then a fuel cell vehicle typically has a battery on board as well, which accommodates accelerations and regenerative braking events. So the two technologies in some way are complementary. On the other hand, one fundamentally takes its energy on board in the form of electrons, and the other fundamentally takes its energy on board in the form of a hydrogen gas or liquid. I have my own views on that. I'll expound on them later if necessary, but I'm sticking with batteries for now.
Do you want to come in, Judith or Serena, on this one or not?
I think it kind of goes back to the earlier question about energy storage as a whole, and for an whole energy system. I think we've been talking mainly about cars, but when we move to an electrified future where we're reliant on renewables, any energy system that we have is going to be hybridized. So you're going to see spots for all of these technologies, and everything is going to have to integrate quite seamlessly together. And that, again, we were talking about interfaces earlier. Getting those interfaces between technologies is going to be a great challenge for not just scientists and engineers, but for companies as well.
Hi, thank you. You sort of asked, the previous question kind of asked what I was going to ask, but I think what I was interested in was where the UK is actually trying to strategically place itself, because it sounds like we're chasing at the heels of things that have already been done. So the gigafactories exist and they're already pushing down the prices. So in terms of like where the Faraday Institution focuses its efforts, is it focusing its efforts on an engineering issue, or is it focusing its efforts on new materials? Because it sounds like the panel is a bit undecided as to whether they can come to meet the targets that the UK has for electric vehicles on the road.
Okay, who wants to quickly answer that one? Serena, do you want to tackle that?
I think, I've shown some of the history of where lithium-ion batteries came from, and there's so much rooted here in the UK, from, the work that Faraday did up to John Goodenough's work on discovering lithium cobalt oxide and the birth of lithium-ion batteries. So we have a rich history from which to grow from. And what the Faraday Institution projects are looking at the moment, it's it's like a mixture of what you're talking about. We're looking at fundamental problems that we're trying to solve in terms of preventing degradation in battery materials, to discovering the next generation of all solid state batteries, to looking at how you might manufacture these materials at scale. So I think there's no one silver bullet to any of this. It's a combination of approaches. And one of the things that the Faraday Institution's done really well is pulling in all of this expertise from across multiple universities, multiple departments, multiple industry partners, policymakers, to try and make sure that we approach all of these problems with a really holistic, in a really holistic way. So it's not just that chemistry is going to make the big breakthrough, or physics or engineering. It's a combination of all of those subjects and all of that expertise that the UK has to offer that will bring about the next generation of lithium.
And it's so often the case, actually. I mean, the UK is actually a very good research base for this. The research is world-class. We need to turn that into world-class ability to deliver this at scale. I think we've probably only got time for 2 quick questions. I don't know who is next here. Yes, thank you.
I have a quick question for Simon, and your wonderful graph on the gigafactory pipeline. I just wanted to know that immediate sort of future capacity that you depicted, is that being driven by any particular battery chemistry? And a quick follow-up question on that, the average cost of the battery, is that being driven by a particular battery chemistry at this moment in time?
Yeah, it's a good question. The vast majority of that, essentially everyone but Tesla, is NCM or NMC chemistry, which is nickel, cobalt, manganese. Now, within that, there are various ratios of that. The industry has gone from 111, which is 30% nickel, 30% manganese, 33% of each, basically, to right now it's 523 and 622 of NCM, the C being cobalt. The holy grail is to go to an 811, which is really high nickel, 80%, really low cobalt, 10%, and that's the holy grail. But the problem is when you build these 811 batteries, you get greater density. The car can go further. It costs more money because you have to build an entirely new line in the battery facility because of the way it's produced is different with low humidity. So that's the trend for 95% of that capacity. Tesla is an NCA. It's naturally low cobalt anyway. It's lower than that 811. I would say those are the things that are driving all of that.
Thank you all very much for a very stimulating talk.
Thank you.